start recording. Okay, here's a problem. You're all here. Okay, everybody's here. Here's a problem. Okay, do it real quick. Pause the video. Okay, all right, there you go. Now we got to find k. 5 halves x is the k value, and from, oops, oh darn it, I gave it away. 2 to 4? Yeah. 2 to 4 on the integral? 2 to 4, right? Natural length of 6, so that's your 0. That's your 0. So if you're going to move it from 8 inches to 10 inches, that would be from a distance of 2 to a distance of 4. Okay, and what was the answer then? Oh, still frozen. How much? 15 what? Inch pounds. Right? 15 inch pounds of work. Okay? All right. And so that's it. I mean, that's basically, we're not going to get much more complicated than that. Just give you information to allow you to find k, or maybe give it to you in another way. Somehow you know k. You can write your force equation into the integral. And again, because this is pounds here, okay, and then again, through small distance, the differential part, the dx part is in, well, not feet in this case, it's inches, okay, and so you get inch pounds, okay. All right, so that's pretty much it. We'll probably have a chance, if you don't have any other questions on the homework ones, does anybody want to see any of those? Throw up the bucket for that. Probably get examples and a chance to do something one or two with you. So one of those two, if not both, could be on the quiz on Wednesday. Okay. All right. So let's talk about the last, really the last new thing we have this year. Now, you know, some of the stuff when we review for the final, for some of you may seem new, but it's not. Okay, it's not. And so, but this, let's talk about this right here. Solving separable differential equations. So as you're writing this down, what is, first of all, a differential equation? Okay, that's not what I asked them. What is a differential equation? An equation with derivatives in it. Okay, it doesn't have anything to do with differentiable. Sometimes I would get that when I would ask you what's a differential equation, like it's an equation where the derivative exists. No, that's differentiable is a function where the derivative exists everywhere. That's differentiable. That's a differentiable function. That's different. A differential equation is an equation, so it has an equal sign, and it's got derivatives in it like this, has a y prime. So it's got an equal sign, and it's got a y prime or y double prime or a p prime or something. That's a differential equation. The solution to a differential equation is what? The original equation y or p or f or whatever, right? So if you got an f prime in it, the solution is f of x equals. And then and doesn't have derivatives in it, right? It does. It's the original function. So what we want here is a y equals. Okay, so so we talked about 3 types of differential equations. We talked about the ones that we can just solve. Now, what does one have to look like where we can just solve it using an antiderivative? What's it got to look like for it to be one where we could just solve it, find the original y by simply doing an antiderivative? No, not, well, Newton's law we memorized. It can't have a y in it or a p or the output variable. It's got to have like y prime equals 3x. Or y prime, equals 2x squared minus 7, or, something like that, right? Where we can just do an antiderivative of both sides, we get y equals, and then we got it, okay? So it can't have a y in it, can't have a p in it, whatever the output variable is, okay? So that was one type. The second type were the ones we were supposed to kind of memorize. Now, there were 2 of them. Y prime equals ky. That does have a y in it. We can't do an antiderivative on that. And the solution to that was what? AE to the KT, your basic exponential function, right? Bank interest, exponential growth of any kind, also exponential decay, those kind of things, okay, could be, would be modeled by that differential equation. And we also had Newton's law of cooling. y prime equals k times y minus some constant t. And then that, do you remember the solution to that one? We just did it the other day. Thought we did. We did an example of it anyway. Big T plus AE to the KT. Well, we're actually going to solve these two types here today. We're going to look at ones like that. So those were two that we just kind of memorized. They're both basically exponentials. This is just shifted up. Room temperature. Remember the room temperature, and it did that. And then the third type were ones we didn't know how to solve, and that's where you would take a class in differential equations to learn all the different types and how you would go about solving them and what the solutions look like. So, okay, we're going to just touch on one type that we wouldn't normally be able to solve, okay, until now we've learned about integrals and so forth, and we can do some things. So, and that is a family of differential equations called separable differential equations. Separable differential equations. Sometimes it's called separation of variables, okay. So like on the AP test, sometimes they'll say, or in our package, sometimes they'll say, use separation of variables to solve this differential equation. Or it might not, it might just say solve this differential equation. That's really the only type we know how to solve, other than this type, right? Now, usually on the AP test, they don't give you one like this. But they could, and so if it's got just x's in it or t's, just the input variable, then we just do it with antiderivative, okay? But otherwise, if it's got y's in it, and they say solve it, this is what they're talking about, because this is the only one we're going to learn, okay? All right. Now, what do we mean by separable? Well, go ahead and open up your books. Go ahead and open up your books to page 441. Okay, on 441. Now, the top half of the page, there are some examples of some differential equations. They have t's and y's, or just y's and whatever. Okay, so here's what we're going to do. So actually, the first thing I want to do is let's go ahead and solve this one. Now, this is we should already know the solution to this one. The solution to this is going to be what? Y equals what? It's right here. It's right here, right? It's the one we kind of memorized, right? And so what is it? A, E to the 3t, because K and K, right? K is 3. Okay, now we don't know what A is. What would we need to be able to figure out what A is? Initial condition, right? Got to be an initial value problem was when they give you an initial condition, and then you can find the unknown constant there, okay, which was the A. All right, so we know that the solution to this should come out to be this. All right, now, so let's go ahead and do it. So here's how this works. First of all, we don't write it y prime, but we want to write it dy over dt. Now, we have no way of knowing if the what the input variable is supposed to be here. Now, sometimes, and this will happen a lot in the homework, they would have given you this problem as y prime of t equals 3y of t. Now, I don't like doing that just because it's just a lot of parentheses and a lot of stuff that's unnecessary. But the advantage to that is it tells us that the input variable is supposed to be t. Otherwise, we're just kind of guessing, right? But since I know this is what it's going to be, I know we usually put a t there, not an x, but it could be an x. I'm not really that concerned about that part of it. But so sometimes they're going to be given to you as this. Just understand, don't be confused by the t part, because that's just there, but it wouldn't have to be there, right? So this is the same as this. But we're going to write the y prime in Leibniz form, and we're going to write dy over dt. And we have to do that. You're going to see why just right now. Because what we want to do now is we want to separate the y's and the t's. We want to get the y's on one side and the t's on the other side. Now, the only way to do that is through multiplication or division. Dividing both sides by something or multiplying by the reciprocal. We cannot move things around here by adding or subtracting. Okay? All right? Because the dy over dt is together with the division, the only way to move one to the other side is through multiplying the dt over to the other side. So that's what we're going to do. So I'm going to move the dt over to the other side. We can do this. This is a legal move. We already have seen it when we were doing U substitution problems. We did the same thing, if you remember. Okay? And so we can do this. Now we got a problem because we got the t's on this side, and we always want, we never want the dt or the dy to be on the bottom, on the denominator. So we're always going to move that over there. So we usually want the y's on the left side, t's or x's on the other side. So I need to get the y over there. So I need to divide the y over. Now you know me, I don't like to divide. I'd rather do it as a fraction. The 3 can go with it, but to be honest, the constants are probably best left over on the right. Constants could be on either side. We want the y's on one side, we want the t's on the other side. The constants can be either place. So usually I will leave that over here. So I'm going to divide by y, which I'm going to write it this way. Okay? And then I get this right here. So that's the process right there of separating the variables. And this is why they're called separable differential equations. Okay? All right. So now, well, just looking at those, they're just begging for what sort of notation on each side. The integral. You got a something dy, you got a something dt. And of course, we know the way to get from a y prime to the original to a y is, by the antiderivative, right? So it just is begging for you to do the antiderivative, the indefinite integral, right? Just do the indefinite integral to both sides. And so what happens, we end up with, what's the antiderivative of 1 over y with respect to y? ln y. Now remember, we would usually put absolute value bars around that. Should do that still. Now normally we would put what else with it? What would we do when we do the antiderivative? Plus c. Now, I'll just go ahead and do it this one time. I'll show you why normally we won't do that. You might be already seeing it. What's the antiderivative of 3 with respect to t? 3t plus c. Okay, now, understand that this c may not be the same as that c, right? They're just some arbitrary constant. If I'm trying to get the y by itself, the first thing I would do is subtract c over to this side, right? Well, what happens if you take an arbitrary constant and subtract some other constant? You get just some other constant, right? C1 minus C2, you get C3, right? So when we subtract this constant over to this side, which we would do every single time, you just end up with a plus c. So from here on out, when I do the antiderivative of the side with the y, I'm not going to put on the plus c. But I will on the other side. Okay, I will on the other side because it would just end up on that side anyway. Okay, now what do I do to solve this? E to this, right? This is a log. E raised to this equals y, right? And again, y's got to be positive here. That's the only concern we have. Well, that's not going to be a problem here. Y equals e raised to the 3t plus c. This will be positive, not a problem. E raised to the 3t plus c. So we can have bars around this, but that is going to be positive. E to the 3t plus c is always going to be positive. So it's not a problem. Okay, so we don't really have to worry about the absolute value bar. Usually don't. Okay? Now, remember, we said the answer was going to be this. Now, it isn't quite that, but actually it is if we just do a little bit of algebra. Let me show you something here. You know when you have x squared times x cubed, right? What's x squared times x cubed? X, you add the powers, right? So it would be x to the 2 plus 3, right? Wouldn't that equal that? Right, so I'm going to do something we don't normally do. Usually when we work x squared times x cubed, we get x to this. Well, wouldn't it be okay to go that way also, though? So if you've got x to the 2 plus 3, that's the same as x squared times x cubed. So this is the same as e to the 3t times e to the c. Would you not agree? Right? Those two lines are the same. right? You would multiply these, you would add the 2 powers. But what's e to the c? What's e, which is a constant, 2.718, raised to a constant? Just some other constant. So let's just call that c. Better yet, we could call it a. Right? So this is just the constant c, or a, and sure enough, that's what we get. And that's where that comes from. That one that we had just memorized earlier. That's how we get it. That is the process of separating variables right there. Get the y's on one side, get the t's on the other side. You start that out by wherever your y prime is, writing it dy over dt. You can separate by multiplying the dt over, get y's on one side, get t's on the other, do the integral, antiderivative both sides, and then solve for y. So if you look on page 441, it's got a series of examples that are separable. So in other words, the first one, dy over dt equals ty. So what can you do? Multiply the t over, divide the y over. Okay, second one, dy over dt equals sine t over y. So we can multiply the y over to the left, multiply the dt over to the right. dy over dt equals sine t squared. Again, multiply the y over and multiply the dt over. Okay, here's some examples of ones that are not separable. Okay, dy over dt equals t plus y. So think about this. dy over dt, or y prime, equals t plus y. There's just no way. There's no way to get the y's on one side and the t's on the other. If you multiply the dt over there, it would have to look like that, right? There's no way to get that y out of there to divide it over to the other side. You just can't do it, okay? So plus signs or minus signs can cause an issue, especially when the t or x and the y are added or subtracted together, okay? Then they give another example where they got sine of t plus y. Once again, there's no way, you can't distribute that, number one, that doesn't work. And there's just no way to separate the t and the y then. Now, one thing you got to be careful of is plus signs by themselves, though, aren't the end of the story. It's not like you can't do it. Like, what if I had 3 plus t here instead of y plus t? Well, now when you multiply the dt over there, you're fine. You got 3 plus t dt, and now you can do the integral. That's like having a 1 there, and now we can do that. Now we got all the t's on this side, and we got all the y's, which actually there aren't any y's, but just 1, and we're fine. Okay, or what if this said, on this side, what if this said 3 minus y? Okay, now we move the dt over there, like so. What could you do now? You could divide by that whole quantity. You could divide the whole quantity, 3 minus y. Now I would write it like this. And then on this side, you just have dt, which would be like a 1. And then you do this. Now what's the antiderivative of this thing? Careful. What is it? ln. This is ln, right? And you have to kick out a -1 too, right? That's an ln. Now we got to be careful. If that was a y squared, you wouldn't be able to do that. Actually, if that was a y squared, we wouldn't even know how to do that antiderivative, so you probably wouldn't end up with something like that. Okay, but I could turn this into this. Okay, what if this is 1 plus y squared? 1 plus y squared. Now you divide this over 1 over 1 plus y squared. What's that? That's arctangent of y, right? That's arctangent of y equals t plus c. And then you can do, well, it's just, you're going to end up with one of those. But that's arctan of y equals what? T plus c, like that. What are you going to do to solve for y? What are you going to do to both sides? What's the inverse of arctangent? Tangent. You're going to do the tangent of both sides. You do the tangent of this side, you get y. do the tangent of this side, you get, right? Now the plus c would be inside the parentheses there. You got to put the plus c on right here when you do the antiderivative, and then you do the tangent of both sides. Now, what I haven't showed you there is if they give you an initial condition, and then you can find c. So let's do an example of it. Okay, so here is you guys try this. Try to separate this and see if you come up with very similar to what we were just talking about with an ln. It's going to have an ln situation, and I gave you an initial condition there. All right, so how are we going to separate it? What are we going to do to separate? I would divide the W minus 300 over. Now, if you want to, you could distribute the 1/25th through them. You could do that, okay? Now, I typically don't. It does go in evenly, so it's not a bad thought. But then the problem with doing that is now you've got to divide the whole thing over, and then you've got this 1/25th in front, so you got to kick that out and do the antiderivative. So I really think the best bet, and just don't pay attention to this on the right, the best bet is to divide the W minus 300 over here, and when you divide it, I would write it as 1 over. And that's always going to be an ln as long as this is not a power, like squared or something. Then you got an issue, but then we wouldn't be able to do it, right? Unless this was just a W squared, you know. Then when we divide that over, we'd have 1 over W squared. Well, that's not an ln. Remember, 1 over W squared is not an ln. That's W to the negative 2, and you do a power, right? Only to the first power on the bottom do you have a natural log, okay? The 1/25th stays here. The dt goes over there like that, okay? So this one's an ln. We don't have to kick anything out. So we have ln of W minus 300. The antiderivative of 1/25th is 1/25th t plus c. And then how do we get the W by itself here? That's e raised to this equals W minus 300. So W minus 300 equals e raised to that. Now, I like to do that whenever I have one of these, I like to split this apart. E to the 1/25th t times e to the c. And that e to the c just becomes an a or some other constant. You could use c. You don't have to use a. But I used a, so I just made that an a. So I get a, on this side, you get a times e to the 1/25th t. So this is going to be a fairly common one you're going to run into with these separable. You're going to get a natural log, so you're going to have to do this. And then here you got W minus 300. Now we could add the 300 over. I chose to just go ahead and put in my initial condition now. Okay, so we put a 0 in for T, so that gives you e to the 0, which is just 1. 1400 minus 300 is 1100, so your A is 1100. So you get 1100 e to the 125th T plus 300. You're solving for the original function. Remember, this is W prime here. We want an equation that's W equals the original equation. Okay, so that is separation of variables to solve the differential equation. All right, let's try one more. Okay, one more. Okay, X is on one side, Y is on the other. All right, so what you'll find is, the first thing that you need to be able to do is separate it properly. Then the more difficult part on some of these is going to be then making sure you don't mess up either the antiderivative or the algebra pieces of it, okay? And that's a big part of it. So this one separates quite nicely. The e to the y divides over, the dx moves over there, and so it looks something like this, but let's talk about this. So when you divide the e to the y over, it's 1 over e to the y. That's not ln, right? That's not ln. That's e to the negative y. is what that is. That's e to the negative y. What's the antiderivative of e to the negative y? E to the negative y with a negative have to kick out, right? You can check it by doing the derivative, right? Do the derivative of this. It'd be e to the negative y, kick out a negative 1, which would cancel that. Now remember, it's with respect to y, so we're not tacking on any y primes or anything. It's with respect to y. So it's just a normal antiderivative. So it's negative e to the negative y, and then this side, that's x cubed. Raise that up to a 2, divide by 2 is 3x squared, and then the plus c. Remember, we don't put the plus c on this side, but we do put the plus c on that side. Then you divide by a negative. So that makes that negative, and I don't care about the c, right? What happens if you divide c by a negative? It's just c, just some other c. Now you can put minus c if you want. They're going to work out fine. So if you wanted to put minus c, you could, but it's just some arbitrary constant, so positive, negative, whatever. Okay, so it's fine to do that. Okay, now what do you do for that? What do you do to both sides now to get y by itself? What do you do to both sides on this? Do the log of both sides, right? Do the log of both sides, and that'll let them do that. So you do the log of this side, and do the log of that side, which will equal what on the left? What we have on the left? E to the negative y, you do the log of it. Negative y, right? Negative y. So you got negative y equals the log of all of that, and then you divide by negative 1, or multiply by negative 1, whatever. So you get this. Okay, and you can just leave it there. Now you could say, well, yeah, you could put that negative up in here, right? You could, and so that whole thing would be 1 over x cubed, negative x cubed plus 3x squared plus c, right? But why do that? I'd just leave it like this is fine. Okay, unless you were doing a multiple choice question, you had to compare answers. Now we put in our initial condition right here. Okay, now a little bit of a lesson about that initial condition. We could have put that in back here. Maybe it would have been easier. I don't think so on this one, but it's sometimes better to put your initial condition in here before you get the y by itself. And another thing you're going to notice on some of ours, where you don't have to always get the y by itself, once you get to here, it's possible that your y, you're not able to solve for y. It's possible you won't be able to get y by itself. And then you may just stop there. Okay, but we could right now put a 0 in for y, e to the 0 is 1, and so we get 1 on this side, and then put a 1 in for x, we get negative 1 plus 2 is 1, 1 plus c, wait a minute, did I do that right? Put a 1 in here, that'd be negative 1 plus 3, I'm sorry, negative 1 plus 3 is 2. 2 plus c, and then we take away 2, we get c equals negative 1. So we could have solved for the c right here and got c as negative 1. I went ahead and just did it here, and we get ln 2 plus c. I divided the negative over, which is still 0, and then I get 2 plus c equals e to the 0, right here. If you put, if you do the e of both sides, right, e to the 0 is 1, so that's where I got the 1 here. And I divided the negative first, so it was out of there. And then I get e to the 0, which is 1, is 2 plus c, subtract 2, you get c equals negative 1. So your final answer becomes that. You put your negative 1 in there. So. Okay, so there's a little bit of algebra and exponentials, the logs kind of working with, and that kind of thing to get your final answer. Okay? All right. Separation of variables. Let's pull out a few of your old packets here and take just a few minutes to finish up a couple of things here. Let's grab the 2014 packet, which we've done most of, except the ones that have separation of variables in them. How many school days we got left until senior last day? How many? 20 around, probably. Because, I mean, what is today? Monday, and your last day is a Wednesday, so are we 4 weeks? Is it 4 weeks from this Wednesday? Around 20. We got a couple days in there we go to school, at least one. 4 days of finals. A couple more days here doing this. about 6 to 8 days of working on our group paper and our final kind of group set of problems that we have. So 8, 12, 14, so there's 5 or 6 more days of just review work, kind of work. Yeah, sounds about right. Okay, anyway, here's 6. We skipped part C. Part C says, find y equals f of x, the particular solution to the differential equation with the initial condition f of 0 equals 1, or y of 0, right? Okay, well that's this problem right here. Find the particular solution. Now the general solution would be with the plus c in it. The particular solution, or the unique solution, is the one you get when you put in the initial condition. Okay? All right, so there you go. Let's go ahead and separate those. This is part C now, and let's see what we get. Okay? How we doing? You got an answer they want to read? Y equals sine x plus 1. No. Yes. Did you say sine negative x? No, negative 3 minus 2 e to the negative sine x. I wrote it that way, but the same thing. Okay? Now, follow my work here. Divide by 3 minus y. That's an ln with a negative. Negative on that y, you got to kick out. So it's a negative ln. 3 minus y. I put the brackets around it. The brackets can go away because y is 1. Since y is 1, you know that that will be positive. Okay, so we're fine. So negative ln sine x plus c, divide the negative over, get negative sine x plus c. Again, it doesn't really matter. You can make that minus c if you want, but it just makes it easier to leave it plus c. You raise that to the e. Now, I went ahead and did it right away, but right up here I did my work. So this would be e to the negative sine x plus c, okay, which would be the same as e to the negative sine x times e to the c. Okay, that's that splitting apart. Happens every time you have an ln, because you're going to have that plus c over there. So you're always going to have e to something plus c. So the e to the c, that just becomes the a out in front. Okay, now, could you have left it up there with the plus c and then found the c? Yes, it's usually more complicated. What the c up there is usually more complicated looking, but it would be okay. They would go through it, on a free response especially, but you oftentimes see this in a multiple choice also, so you got to be able to know that. Okay, so that's where this a comes from, or a big C if you want to put it there, that's fine. Subtract 3 from both sides, divide by a negative, you get that. Then you put your 0 in, so sine 0 is 0, e to the 0 is 1. So you get negative a plus 3, and I did that up here. Negative a plus 3's got to equal 1. So a would equal 3 minus 1, or 2. So a becomes 2, and then that's where you get it. Okay? All right. So in the package, usually when you have a differential equation, it's got x's and y's in it, or maybe just y's, and they say to solve it, they don't have to say, matter of fact, they've moved away from that. They used to say solve by separating variables or solve the separable differential equation, and they've kind of moved away from that. And I don't know why. I guess maybe because they just thought telling you that was confusing. I don't know. Saying to separate variables, since that's the only real way we have of doing it. So a lot of times now they just say solve the differential equation. That's how you do it. Okay? All right. So for homework, I'll let you go ahead and work here. We got a few more in the package we've skipped, but we'll take a look at those and have a good review tomorrow. So the 7.4 line on your homework has got some differential equation problems to do. When you get going. So do you want to do it tomorrow? 27. I mean, yeah. So we need to put. Yeah,
I think it's below right now.
For high school paper. Yeah, I think it's good.
That's what I was shooting. Wouldn't that another one? That's 5.
Like the 2015.
What's that, John?
It's like 2015 example 4.
What happened to like the core 2?
We got some.
The 2 hooligans.
And you're going to be going through there.
So Wednesday.
Please call them and Jackson.
They are.
It's gonna be some worksheets, and I'll just post it. Sounds good, thank you. Yep.
No, you questions for Mr. Jackson.